Hey everyone, my name is Jake, and I'm a developer at Privacy and Scaling Explorations. And today we're going to go over validating ERC-4337 UserOps using zero-knowledge proofs. For our agenda, we're going to go over why we are using ERC-4337 and zero-knowledge proofs and what they open up. We're going to go through validating UserOps via ZKP, including a kind of partial overview of 437, which is a leading account abstraction spec in the Ethereum space. We're going to cover then stateful validation inside of 437, and then we should have time for wrap-up and questions. So I'm a member of the WAX team, which includes our team lead James, Andrew, and John, and we work, we're all wallet account experiments, and we do a lot of experimentation with account abstraction in 437 recovery options and validation mechanisms. So, why do we want to use 437 and ZKPs for validation? By a show of hands, how many people use a smart contract account today for something significant? All right, a pretty good share, but not everyone. Inside of the Ethereum ecosystem kind of today, we have the externally owned account, or the EOA, using ECDSA signatures. And this is the vast majority of accounts, including on layer 2s. And frequently, people will lose their keys, have them stolen, or get locked out of their account and lose access to funds or other digital assets they may have. And we do have some flexibility in the different options we can use, but in general, people do not use a lot of these and just simply have like a single seed phrase controlling things. And so when I think about this, and I'll complete this analogy in a moment, I think of these as kind of these single-celled organisms of accounts today. But imagine if we lived in a world where you could approve transactions and potentially recover your account if you lost your keys via a variety of different mechanisms, which could be something like a government ID or a passport. You could be part of an anonymous group where you couldn't find an individual member, but they could help you recover or send something. You could use something like an image, a video, or your voice in order to approve or recover. And finally, as we just saw, something such as easy as sending an email. And so I think that takes us from this more kind of simple, basic one type of account into almost a Cambrian explosion of different account types and a bunch of different, almost like life forms living on chain doing things like that. We already know that we can do things with ECDSA, we can do things with BLS signatures, and we've seen a lot of development recently too with using passkeys or with the WebAuth and spec. But we also could open up a lot of different options as well, including things we may not have even thought of before. And so with that, let's jump directly into validating those UserOps via zero-knowledge proof. So we're going to focus on a very specific segment of 437, which has to deal with the validation of UserOps. You can think of user operations as essentially pseudo-transactions. As part of the accounts you have as part of 437, you implement an interface, which is this iAccount interface. And all it does is simply take a user operation and some additional data and just lets the entry point know if it's valid or not. And as part of that user op, we have a signature field, which can be just any arbitrary bytes. In practice, this generally is a cryptographic signature, but it can really be anything we want it to be. And so, taking advantage of that, during creation for the user op, we can put a proof inside of that signature. And so, with say a 437 SDK in a wallet, a prover, and our public and private signals, we can then construct a user op where that signature would be that proof and potentially other public signals that are part of that. We then will submit that to a bundler, which we'll get into in a moment. An example of this might be something as simple as a password. Normally, if we were to put a password in that signature field, as soon as we send that first user operation and it gets submitted on chain, anyone would be able to extract that password and would be able to use our account. But inside of a private input for a proof, we could use a spooky emoji sequence, such as this, as well as a public signal of the hash of our user op to make sure that this proof would only work for that operation. We can then ABI encode that proof and put it in the user op, and in this specific case, we do not need additional public signals, and then submit that once again to that bundler. Finally, inside of that bundler, it's going to collect the user operations not only from our wallet, but potentially a large number of wallets into either a private or public mempool, in which it will run simulations to see whether those are valid to run. Once that's complete, it will submit one transaction onto an EVM chain that has a singleton entry point contract deployed that is able to process those for an account. It forwards those to the account, and then for that account, we can attach a verifier, such as one that would be generated by Snark.js with a CIRCOM circuit, and we can take that proof that we encoded, as well as maybe additional public signals we may want as part of that account contract, and run that into that verifier contract. And then finally, if that passes, during our execution phase, we would have our actual contract interaction or send out. And so yeah, that's it. We're all done. Easy peasy, and we're good to go. So to wrap up, we're gonna, it looks like my presentation had an error. Let's see what this is. Account is forbidden read from, looks like a contract address at some storage slot. I wonder why that happened. And that takes us right into stateful user op validation. It turns out in 4337, during validation, you cannot do a lot of things. And one of the biggest ones is you cannot access storage that is outside of the account that you're validating for. You can still call to other contracts and other contract code, but you cannot access storage inside of those. There are also many opcodes, call opcodes, gas opcodes, and block properties, and many more that you cannot use inside of validation, and some exceptions apply. The reason for this is that during validation, you may have user operations that would pass inside of the bundler and that it will submit. But once it actually goes to submit them on chain, if those contract storage slots were to change, you could potentially have a mass invalidation of user operations happen, even though the bundler spent all this time to bundle them together and submit them on chain. And this is actually an attack vector the spec takes into account to prevent DDoS attacks on the bundler network. And so that is why we cannot access those things. And so this is very problematic for ZK verifiers that need state. Some common things would include a Merkle tree root, or common rotatable public keys, such as an SSL certificate, or an email DKIM public key, such as that used by ZK email, and there's others as well. However, we can access certain storage in the account contract. We can access storage in the actual account contract, so that contract that's deployed, but we can also access storage associated with the account address from another contract, as long as it's associated with only that address. In practice, this usually is a mapping of, say, that address to some structure value. And so one of the more common cases where you may want to do this during validation is you may want to do validation based on checking for, say, NFT ownership. Or you could do validation based on a certain ERC-20 token balance. The final thing we can do is we can essentially specify an aggregator contract, which we'll talk about near the end of the presentation, in which you can tell the account contract to use that other contract as its validator rather than the account contract validating itself. And so, now that we know kind of what we can't do, but also what we can do, we can kind of have two general purpose solutions for how we can access storage during this validation phase that would be helpful for these more stateful verifications of zero-knowledge proofs. Number one is that when you have an update of, say, that key, you just push that to every account, or in that mapping, push to every slot for every address that you want to track. And number two is that we implement an aggregator, which we'll go over what exactly that involves. So as an example for this, we're going to use the DKIM public key that's needed by ZK email. So, first off, we're going to have the push updated state. And so there are two key steps to this. Number one is, so we're going to have our contract with whatever kind of, let's say, for example, public key we want to store. That contract will accept updates of that remote key into there. And then we also need to keep a list of every account we care about that we want to update. And when we update that key, we need to do one of two things. We either A, needs to update all of the mappings inside of that contract for every single account to that new key, and then we can access that during validation. Option number two, or B, is then using a permissioned function to say update the accounts directly, which may have that actual verifier attached to them. And so the pros of this approach is it's really simple to implement. This would be kind of almost like a beginner or intermediate Solidity problem to code up. And as I mentioned before, you will have certain throttling and banning scenarios to prevent DDoS attacks. And in this case, it's not subject to those. So if you need to update that key more frequently, you would be able to do that without being penalized. But there are some cons to that as well. And that includes the need to track each individual account. And the more accounts that you have, the more compute and storage costs that will be associated with updating that. But that is less relevant on, say, a layer 2. The other option is to use an aggregator. The aggregator entity is essentially a contract that can validate UserOps, both one or a bulk UserOps with an aggregated signature. It also can take a large number of signatures and aggregate them into one. The most common use case example that's done with this is for aggregating BLS signatures. And so to implement this, we would implement this interface on a contract. And for this signature aggregation, if you actually don't want to aggregate the signatures, or potentially even aggregate the proofs together, you can just concatenate all the proofs together into one very long aggregated signature. And then we just simply need to have the account during validation do a revert with the validation result with aggregation error. And then on our aggregator contract, we can just update state as needed. And so what this looks like is we have our aggregator with its key. It's attached to our verifier. We have our accounts verify that they would like to use that aggregator. When we have updates, such as a rotation for that key, we can then push that into that aggregator as just one simple operation. Then, when the bundler gets a lot of UserOps that are using that aggregator, it can request that it aggregates those signatures or proofs together, and then it will construct a batch that goes through an aggregated entry point into there. And so through that, we're able to have that kind of common field that they're able to use and still update it. But there are some trade-offs with this as well. So you have very simple state updates. Many accounts can use just one contract for verification rather than having it inside of the code for each one. And there are a lot of optimizations that bundlers can do in how they group these together, including things like running non-EVM cryptography libraries to make the performance of bundling those together faster. But the downsides are that it's much more complex to implement. You may not need signature or proof aggregation, but you still need to implement some way of doing it. In addition, that aggregator contract needs to be staked in order to prevent, oh sorry, I didn't do that. It needs to be staked in order to be slashed or be able to be throttled or banned if it is malicious and if it's constantly invalidating user operations and causing the network to suffer. So you need to have that staking, and you're obviously subject to that. So you cannot update that state as frequently as you could do with the other solution. So to wrap up, some key ideas to take away. So with 4337 and zero-knowledge proofs, it opens a wide space for experimentation and exploration with a lot of with Ethereum accounts. Number two is that doing stateless ZK validation is actually relatively simple and easy to implement. And finally, stateful is harder, but we have at least two solutions we can use to work within the 4337 specifications to do that. If you're interested in learning more about WAX and some of the experiments we're doing on top of accounts, you can go to wax.psc.dev, where we have our public repos, a Discord server where we'd love questions, and an in-page demo of some of the accounts we've implemented. Thanks, everyone.